Welcome to the last day of the conference. The first speaker for today is Bruce Berndt from University of Illinois at Urbana-Champaign. He'll be talking about the circle problem, the divisor problem, Bessel function series, and Ramanujan's lost notebook.
Thank you very much, and I would like to say this is a great honor for me to be chosen to speak at this conference on number theory and physics, and I'm very grateful for the invitation. My preamble will be a bit longer than usual. So I actually began my undergraduate career majoring in physics. After 1 year, I decided that I liked mathematics better, so I continued to major in physics, but I made mathematics my primary major. And I went to a small liberal arts college, and almost all of my mathematics and physics was taught really by 3 people. So I'd like to dedicate this talk to their memory. 2 of them just passed away within the past 2 years. And this work on which I will lecture is work I've been doing with Sun Kim, a former graduate student of mine, and my colleague Alexandru Zaharescu. Started about 10 years ago, but then Sun with Alexandru and myself, and then Sun joined us about 5 years ago, and then we made much more progress after she joined us thinking about these problems. So Oya Chan is one of my former students, and he did the calculations, which I'll describe toward the end of my lecture. So this is a picture of Sun Kim. She got her PhD at Illinois under the joint direction of Kevin Ford and myself 5 years ago. And she was probably the best female student in number theory we've ever had at the University of Illinois. However, she is still without a tenure track position. So if any of you want to hire a great female number theorist, I strongly suggest you make an offer to Sun Kim. And this is my colleague, Alexandru Zaharescu. Okay, I'd like to begin with this quote from Vivekachudamani, a book by Adi Shankaracharya in the 6th century. I have shown you today the highest secret of my own realization. It is supreme and most mysterious indeed. So I'm sure that he was talking about Ramanujan's lost notebook, a very prophetic voice from the 6th century. So I should give you this is one of the 4 photographs that exist of Ramanujan. It's by far the most famous photograph. It's the passport photo that was taken prior to his return to India from England in 1919. So it appears here that he has a suit coat on, but in fact, this is a bathrobe. This picture was taken in his pajamas and bathrobe at the nursing home where he resided because he was too sick to go to the photographer to have his picture taken. So this information came to me from Robert Rankin, who was Hardy's last PhD student. Okay, so now I'm ready to begin my lecture, and so my lecture will concentrate on these 2 formulas from Ramanujan's lost notebook. So you needn't squint your eyes too much because I will actually give them to you in LaTeX version. So let me discuss the first one. So we define cap f of x to be the floor function or greatest integer function if x is not an integer, and then its average, x minus a half, if x is an integer. Actually, in the lost notebook, Ramanujan uses square brackets x for f of x, but since that's an unorthodox notation, I have changed this to a more orthodox one. And then if you saw some j's floating around the first formula, these are ordinary Bessel functions. So here is the first of the 2 formulas, and I will show that this is connected with the famous circle problem. So theta is between 0 and 1, and x is positive. And then we have this identity for a double series of Bessel functions. So analytically, it's a very curious identity, because note that if x is fixed, then this is just a finite trigonometric sum, because f of x over n will be 0 for n sufficiently large. So the identity says that this double series of Bessel functions can be simply expressed in terms of a finite number of sines plus a couple other elementary functions, something you certainly wouldn't guess from looking at the double series of Bessel functions. So it's also not clear that this double series actually converges. So let me just say a few words about that. So this is a well-known asymptotic formula for the ordinary Bessel functions as x tends to infinity. So if you just use this asymptotic formula in the terms of the double series, you see that the series terms asymptotically are of this type. And so it's clear that the double series does not converge absolutely, but there's a chance that it might converge conditionally. But you see, it's going to be very difficult to show this because the m and n are intertwined together under the square root in the trig functions. So indeed, the convergence of this double series is very difficult to show, and in particular, one needs to show that it converges uniformly on compact intervals when x is greater than 0. And so this causes lots of difficulties for us. Yeah. So now let me indicate the connection of this identity with sums of squares. So we'll let R2 of n be the number of representations of n as a sum of two squares, where we count different signs in the summands as being distinct. And then we also count different orders as being distinct. So for example, then r sub 2 of 5 is 8, because 5 is 2 squared plus 1 squared, but you can change the signs in 2 squared different ways. And of course, you could change the order. So there are 8 different representations for 5 as a sum of 2 squares. So each representation of n as a sum of 2 squares can be associated with the lattice point in the plane. For example, if 5 is minus 2 squared plus 1 squared, we associate that with the lattice point minus 2, 1. And then we associate each lattice point in the plane with a unit square. It doesn't make any difference which of the 4 unit squares we take, but we should be consistent. So I've chosen the one in the south, so that the lattice point is in the southwest corner. Yeah. Okay, so if I want to sum R2 of n over n less than or equal to x, that's really then the same as counting the number of lattice points in a circle of radius square root of x. And then numerically, that's the same as counting the areas of these squares, red squares, where the lattice point is in the southwest corner of the square and lies inside the circle of radius square root x. That. Okay, so the sum of R2 of n less than or equal to x, then is the sum of the areas then of these unit squares. So of course, these can be approximated, the sum of areas, by the area of the circle. So we have then that the summatory function is going to be pi x plus some error term. Now I've put a prime on the summation sign to indicate that if x is an integer, then we count only 1/2 of the summand. And the reason for this is that if one uses Fourier analysis or complex analysis, this is the sum which naturally arises. And as we'll see later, it doesn't really affect the error term as to if we count 1/2 or all of the terms R2 of x. Yeah. Okay, so this problem originated with Gauss. In other words, what is the order of the error term here if we approximate the sum by pi x? So Gauss gave this very simple argument. Certainly all of the squares are in a circle of radius square root x plus square root 2. Okay, so an upper bound would be pi times square root x plus square root 2 squared. And then clearly, then if you take a circle of radius square root x minus square root 2, that will be entirely covered red in my picture. So in other words, a lower bound would be pi square root x minus square root 2 quantity squared. And then combining these together, you see that r of x, the summatory function for r2 of n, is pi x plus big O of square root x. So Gauss gave then the first estimate or upper bound for the error term in the circle problem. Okay, now there's a famous formula of Jacobi for R2 of n. So it's 4 times the number of divisors of n congruent to 1 mod 4 minus the number of divisors congruent to 3 mod 4. Yeah. So if you take the summatory function and then substitute in Jacobi's formula, but I will write the Jacobi's formula for R2 of n in this equivalent way. And then you see we're summing then over all products dj less than or equal to x in this sum. So if we sum on j first, that's clearly square brackets x over d. Yeah. Okay, so now note that this is very familiar in terms of the summatory, the function on the left-hand side of the identity that I gave you. In fact, it's just the special case when theta is equal to a quarter. So in other words, the trigonometric sum on the left side of Ramanujan's formula is a generalization of this representation for the summatory function for R2 of n. Okay, well, there's another formula for R2 of n, or the summatory function, in terms of Bessel functions. And this first appeared in Hardy's paper in 1915. And he said in the paper that Ramanujan showed him this formula. Yeah. So we don't know Ramanujan's argument. The circle problem was first improved by Sierpinski in 1906. And he showed that the error term is big O of x to the 1/3 as x tends to infinity. So that was the first improvement since Gauss. So he did not use this representation for the summatory function, but a weighted representation then. So this identity predated this identity, and again, probably Ramanujan was the first to prove that identity. So the advantage of this identity is that this series converges absolutely and uniformly on compact intervals for x greater than 0 and is easier to work with. Of course, what one has to do is work one's way down from this weighted sum until the sum of R2 of n. Yep. So this is what Sierpinski did, and then Landau also did a few years later, simplifying Sierpinski's ideas. Yeah. So let me just give you a brief history of results on the circle problem. So we'll write the error term as big O of x to the a plus epsilon, and for epsilon greater than or equal to 0. So usually most of the results involve logs, and I'm just ignoring all these logs, and I'm just handling them by an x to the epsilon. Yeah. Okay, so here we have then starting with Gauss and then Sierpinski, and you can see then very small increases in the, or decreases in the order of the error term. And here are the last three. So currently the best result is due to Huxley, and the A is 131 over 416. Yeah. So if any of you know of results that I've missed in the catalog that I've given you, please inform me of any that I've actually missed. Yes? That was for the divisor problem. Yeah, I'll get to that. So you see that in over 100 years, we've made a little less than 0.02 improvement on the order of the error term in the circle problem. So I understand that these meetings on number theory and physics are planned for every 2 years. So at the 50th meeting in 100 years, please invite me back, and I'll tell you about the improvements. Hopefully we've knocked off a 0.02 in the next 100 years, but it's probably doubtful then. Okay, so let's look at it from below. So I'll use a familiar notation in analytic number theory. So we have g of x is a non-negative function, usually of a simple type, like a power of x, say. And there are three different omegas, so I'll only concentrate on the first. If you want to keep track of the sign, then you look at these other two. So we say that cap g of x, so this is the function we want to sort of bound from below, is omega of small g of x if there exists a positive constant k such that the absolute value of g is greater than k times g of x on some sequence of xn's tending to infinity. Then. So Hardy, in the paper in 1915 that I mentioned a few minutes ago, showed first of all that the error term is omega plus or minus x to the 1/4. So this shows that the error term is at least x to the 1/4. But then here in the same paper, he showed it's omega minus of x log x to the 1/4. So most people feel that Hardy's result is closest to the truth. In other words, the conjecture is that P of x is big O of x to the 1/4 plus epsilon as x tends to infinity for every epsilon greater than 0. So let me just tell you about a few improvements. So on the plus side, Gangadharan added a log x to the 1/4 and a triple log to the 1/4. And his result was improved very slightly by Karate and Katai. And then Hardy's result was not proved until 1981 when my PhD student, Jim Hafner, added essentially a log to Hardy's result. Now I should stop here and give credit to Atle Selberg. So in 1973-74, I was at the Institute for Advanced Study, and I went into Selberg's office one day, and we discussed the circle problem. And he said that I improved Hardy's result, and I wrote it up in a manuscript. So this was really very interesting to me because I knew that nothing had been published improving Hardy's result. And he looked all around his office for his manuscript, and he couldn't find it. However, he showed me, he mentioned in a couple sentences what he had done. So I remembered these sentences, and then some years later told them to Jim Hafner. And then with the help of a little correspondence with Selberg, he then got this improvement, which is the improvement that Selberg had found. And then Soundararajan improved Hafner's result, and so currently Soundararajan's excuse me, result is the best that we have. See, is there any water around? So just comparing the powers of log x, you see on Hafner's result we have 0.1732 and Soundararajan 0.1949. So these are the best results that are known for the circle problem. Now, Hardy, excuse me, Hardy in his omega proof used actually this identity then. And then at the end of his paper, he said that Ramanujan showed him this identity then. So this is really a beautiful identity. Note that you get from the left side to the right side by just interchanging the A and the B. So if you don't think that's a beautiful identity, you're just not a mathematician, I don't think. I think that's just a beautiful identity. So in fact, Hardy then proved it, and he actually replaced the R2 of n by the number of representations of n as any positive definite quadratic form in two variables. Now, if you differentiate this with respect to b, and then you let a tend to 0, and you just redefine the parameters a and b, you can easily see that you get this identity. So in fact, Ramanujan's identity is actually a generalization, after differentiation, of the identity that Hardy used in his work. Yeah. So there are two sort of main contributions of Ramanujan to this paper, and I suppose, you know, if I were Hardy, I would have made Ramanujan, you know, co-author of this paper, but, you know, maybe customs were a bit different in that day. Okay, so now let me get back to the original identity, and I can say that this is now proved by Sun Kim, Zarescu, and myself. I'm sorry I forgot to give the reference. It was in Advances in Mathematics in 2013. Yeah. But before that, Zarescu and I proved the identity with the order of summation reversed. So we did this in 2006, and then we didn't make any progress on the original identity, as I indicated, until we invited Sun Kim to work with us. Now, it turns out that the identity with the order of summation reversed is easier, but still difficult to prove. And what we did is to get rid of the Bessel functions. So we then showed that it was equivalent, and this was an equivalent identity involving these trig functions then. So then, as I said, we proved that equivalent identity. So now, I mentioned a few moments ago that the summatory function is really a special case of the identity when theta is equal to a quarter. So if we put theta equals a quarter into the identity, then we get this representation for the summatory function in terms of this double series of Bessel functions. Then what we did at that time in 2006 was to go back to Jacobi's formula, take the Hardy-Ramanujan series for the Bessel functions, and substitute in for R2 of n Jacobi's formula. So then separating the divisors of the form 4n plus 1 from those of the form 4n plus 3, we then got that the summatory function is equal to this series of Bessel functions. But note that I'm glossing over a problem here, because in the original identity, we're summing on m first and then n. But then when I make the substitution, the m and n are tending to infinity together. In other words, no longer do I have an iterated sum. So I am assuming then that the order of summation can be changed to this more symmetric sum than when the m and n are tending to infinity together. So then this leads us to the question, maybe Ramanujan thought of this identity with m and n tending to infinity together, and he just stated it in terms of an iterated sum. So we then went back and then we reproved the identity in a symmetric version. So as you see here, now we have the upper index of the sums on n and m to be the same, and so we proved the identity in this way as well. Yeah. So let me just summarize then. There are three ways of interpreting the identity. We have the iterated double sum, where we sum on n first and then on m. This is the way that Ramanujan stated the result, and about 2 or 3 years ago then we proved the result as Ramanujan stated it. And then we had proved the identity with the order of summation reversed about 5 years earlier. And then we've also proved the identity then wherein the m and n tend to infinity together. And I put a question mark after Ramanujan's name because it's possible that he actually interpreted the double sum in this way, but we don't know. So you might ask, well, can we just show the inversion directly? Can we get from one order of summation to the other? And the answer is probably no. The methods that we use for each of the three theorems are entirely different. We don't use anything from one proof in any of the other two proofs. So let me just briefly give you some ideas of the proof in the symmetric version and the proof of the original version. So the proof in our symmetric version and actually our original version that Zaurescu and I proved used weighted divisor sums. So chi here is a character modulo q. It's actually going to be a primitive character. So you can easily check that if you take the sum of f of x over n times this character, you actually then get this divisor sum, weighted divisor sum. So then what we did is to use a continuity argument, and we took theta to be a over q, a rational number, and then this is a dense set, and using a continuity argument, which again is not easy to show, we proved the identity for rational numbers theta equals a over q. And then along the way, we needed actually this formula for the summatory function for the divisor function. So L of 1 chi is just the ordinary Dirichlet L function evaluated at 1. So I have not found this result in the literature. It actually comes from a special case of a result I proved in my PhD thesis many years earlier. If any of you have seen this result in the literature prior to our using it a few years ago, I'd be very grateful for this information. So no, usually, your PhD thesis is good for finding a job, and you just, sort of forget about it. But, here I've used my PhD thesis over 40 years later in a very important way. So I hope all of you will be able to use your PhD theses, later in your life, as I have had this privilege. And then we converted that sum into a sum of double series of Bessel functions. So let me just say just a very few words about the proof of Ramanujan's formula in its original form. So what we did is to use the asymptotic formula for Bessel functions, and we singled out that part of the formula which gave us the main stuff. There are terms for the identity. And then all the other things we had to approximate. So we had to actually develop new methods for actually estimating trigonometric sums. So in particular, as many of you know, if you have a trigonometric sum and you're summing up to x, if you get square root x cancellation, that's really good. However, for part of our work, we actually needed better than square root x cancellation in the trigonometric sum. So we had to develop another method for estimating these trigonometric sums. And then there's another part of our work in estimating the trigonometric sums where we got rather depressed because we thought our methods were going to fail. And I'll just briefly indicate where that was. So we came down to a sum that we thought should, go to 0. And I'm sort of skipping all the details, but we approximated the double sum by a double integral, and we evaluated the inner integral, and we got this. And then a miracle occurred. Namely, that this integral is actually 0. And then everything was okay, and we were able to go on. Now, if C0 had not been 0, our method would have collapsed, as we wouldn't get enough cancellation in the trigonometric sums that we were estimating. So the 3 pi over 4 was crucial. So if you replace the 3 pi over 4, this is actually an elementary integral, you can see, in fact, you won't get 0. And where does the 3 pi over 4 come from? It comes from the asymptotic formula for Bessel functions. So if in that asymptotic formula for Bessel functions, there weren't this 3 pi over 4, but some other, like pi over 4 or something, then everything would have collapsed. So usually when one uses asymptotic formulas for Bessel functions, one sort of ignores that constant which comes in the argument, but here that was really crucial for us. Okay, so I think that's all I will say about the circle problem, and I'll now go to the second identity in the Lost Notebook and the Dirichlet divisor problem. So I have used 34 minutes, but I won't use 34 minutes on this problem because some of the ideas are repetitive, and so I won't actually repeat some of the ideas. Okay, so let me describe the Dirichlet divisor problem, which was discussed briefly by John Keating in his opening lecture. So d of n is the number of positive divisors of the positive integer n. And then the summatory function d of x is equal to x times log x plus 2 gamma minus 1. Gamma is Euler's constant. So this quarter here, you might say, what's that doing here? It just, as we have a representation for the error term, delta of x, where that 1/4 is natural. Of course, in terms of the error term, it's inconsequential. Yeah. So finding the correct order of magnitude of the error term, delta of x, is what is called the divisor problem, or Dirichlet divisor problem. And historically, whenever there is an estimate or upper bound for one problem, the same methods normally work for the other problem as well. So the chronology of upper bounds that I gave you earlier for the circle problem has an identical chronology for the divisor problem. The only thing that might be different are the logs that appear in the upper bounds. Yeah. Well, I'll give you Dirichlet's argument as to how we obtain the main terms here. Okay, so this is the I'm just using the definition of d of n here. So again, writing n as a product dj and summing on j, you get this. And then note then that what we are doing is just counting the lattice points then on vertical lines underneath the hyperbola. I have it yz equals x. So what Dirichlet did was to take a square of of side square root x, and then counted the lattice points in regions 1 and 2, and then he counted them in regions 1 and 3. Of course, that number is the same. And then we subtract off the number of lattice points in region 1, which we've counted twice. Okay, so here is then Dirichlet's argument. So here is our summatory function. And we break them up into two sums, regions 1 and 2, and then 1 and 3. And then we subtract off the number of lattice points in the square of side square root x. Then we just replace the square brackets x over d by x over d plus big O of 1. Here we replace square brackets of square root of x by square root of x minus the fractional part of x. Okay, then of course this sum is just big O of square root x. And now we're left with just the partial sum of the harmonic series, and we just use a familiar formula for estimating a partial sum of a harmonic series. Okay, so that gives us this result, and Dirichlet then showed that the error term is big O of square root of x as x tends to infinity. So that's the first estimate we have, again, just in analogy with what Gauss did. Okay, now let me get to Ramanujan's formula and also Voronoi formula for the summatory function. So I'm going to use Ramanujan's notation here. So I'll let y nu of x be, as usual, the Bessel function of the second kind. And k nu of z is the modified Bessel function of order nu. And then after Ramanujan, we'll set I nu of z to be minus y nu minus 2 over pi k nu. Then Voronoi in 1903 showed that the error term, delta of x, can be represented by this infinite series of Bessel functions. And he showed that delta of x is big O of x to the 1/3 log x. So this was then the first improvement on Dirichlet's result. And as I mentioned earlier, then further improvements follow along the same lines as the improvements for the circle problem. Now let's go to Ramanujan's second formula. So I remind you of the definition of f again. So this is the second entry on the page I showed at the beginning of the lecture. So now instead of having a finite sum of sines, we have a finite sum of cosines on the left-hand side. These functions have changed a bit. And the Bessel function, J1, has been replaced by this linear combination I1. So again, analytically, it's sort of an interesting formula because you have this double series of Bessel functions represented as just a finite sum of cosines plus some elementary functions for each fixed x. Now, there's one difference in this formula than in the first formula that I would like you to note, and that is there is a plus sign here, whereas in the first formula there was a minus sign. And that actually turns out to be important. So the Bessel functions y nu have the same sort of asymptotic formulas as the ordinary Bessel functions, and the modified Bessel functions decrease exponentially as the variable tends to infinity. So for our purposes, they really can be ignored. So let me indicate why things are more difficult for this identity than they were for the first identity. Well, first of all, k nu and y nu have singularities at the origin, whereas the Bessel functions do not. So these cause difficulties. So originally, Zararescu and I inverted the order of summation and found we could give an easier proof, so to speak, for the identity with the order of summation reversed. We can do that here, but we do not obtain nearly as nice of an identity. I will show you the identity in just a few moments. And then, so to speak, this is a very rough terminology, there's no cancellation in the pairs of Bessel functions because I have this plus sign instead of a minus sign between the Bessel functions. So all three of these facts and some other things cause difficulties that we didn't encounter previously. Yeah. Okay, so we were able to prove the identity with the order of summation and reversed. And also we proved the identity in symmetric form, but not in the order in which Ramanujan originally stated the identity. So here is the identity that we get when we invert the order of summation and we get rid of the Bessel functions. So you see it's much more complicated than before, and we have to group together these signs and these integrals because individually they do not converge separately. That is, individually they do not converge. So we have these limits, these two limits where we have to take the sum and the integral together. So this causes analytical difficulties. So let me just summarize here. For the order of summation reversed, those individual series and integrals diverge by themselves. So this causes difficulty. And again, I emphasize we've interchanged the order of summation. And then, very importantly, we had to assume that we had convergence for one value of theta. If we have convergence for one value of theta, then we showed that we have convergence for all values of theta between 0 and 1. Now you might say, well, this should be very easy. Just take one nice value of theta for which you could show convergence, and you can remove this hypothesis. But we cannot find a nice value of theta for which we can show the convergence. Now, so Zararescu and I have a different opinion about our theorem. So he's very proud of this because it's a new kind of theorem, showing, well, if you have convergence of one value, you get convergence for all values in the interval. To me, it's a blemish. In other words, we had to, assume that we have convergence at one value of theta. Now, so again, there are three possible orders of summation, and let me just summarize. We have the iterated double series, as Ramanujan stated it, and we do not have a proof of the identity as Ramanujan stated it. So we sort of let it go for a couple years, and I think we'll return to it in the coming year. And then we have the iterated double sum with the order of summation reversed. So in other words, we're summing on m first and then n. So we have proved this. And then we have proved the result when the upper indices of the sums on m and n tend to infinity together. Now, let me just briefly indicate some numerical results about the convergence. So we'll put everything on one side of the identity except the double series of Bessel functions. And then we'll calculate some partial sums on m and n. So let me just go to my second slide here. So let's note here, we're taking m to be 500 and here 1,000. So here is the left side. And note that here we get a better approximation at 500 than we do at 1,000. And the same is true here. So this is, doesn't give one optimism. But on the other hand, we have shown, these are just finite sums, and we have shown the identities hold in the other two regions, but for the other two methods of summation. But there is some further evidence in the way that for the sum in which Ramanujan stated it, that it might not be correct. So we're not 100% certain that the Ramanujan statement is actually correct. So then we ask our... Yeah, so the only reason we think he might have thought about the symmetric sum is because of the arguments that I gave substituting in Jacobi's formula. But we have no idea as to how Ramanujan thought. We just have the identities themselves. So just because of the use of Jacobi's formulas in getting a more symmetric sum, we think maybe Ramanujan probably saw this, and so maybe he considered the sum symmetrically, but we really don't know. Yeah. Okay, so Rescue Sun Kim, and then I thought, well, are there any other results of this type? And we actually did prove 3 further results of this type. So here we have an identity for a product of 2 cosines summed over all products n and m less than or equal to x. So the theta and sigma are independent. They're both between 0 and 1. So here we have a double series of Bessel functions, and I should have maybe been a little more careful here. I just said m and m greater than or equal to 0. The sum is symmetric. In other words, the n and m are tending to infinity together, so to speak, in this identity. Yeah. And to prove that identity, we used weighted character sums. So now we have 2 characters in our sum. So chi1 and chi2 are non-principal, even primitive characters modulo p and q. And then we have this identity for this these weighted characters. So again, I have not seen this identity in the literature, but it follows from a result in my PhD thesis. Unfortunately, when I wrote my thesis, I didn't realize these interesting special cases, and we only worked them out in our work recently. Yeah. I'm going to make a bold conjecture here that as x tends to infinity, this double sum is big O of x to the 1/4 plus epsilon for every epsilon greater than 0. Yeah. So we did not actually make this conjecture in our paper, but I thought I would just throw it out. And I have a graduate student thinking about this a bit. And then we also have identities for cosine sine and sine sine. You note here that I have an n and m. So these arise from odd characters and from your knowledge of Dirichlet L series and the corresponding theta functions for odd characters. The n and m are probably not surprising. Yeah. So this work appeared in Krella a couple years ago, but as I said, we didn't make that conjecture in this paper. So let me just close with a few words about finding the order of error terms for arithmetic functions in general, and I'll state a couple more identities. So suppose you have an arithmetical function a of n, and you want to find the average order of this function, of the summatory function, or the average order of the function, or then an asymptotic formula with error term for the summatory function. Okay, in the cases that we've looked at, we actually have infinite series of Bessel functions in our representations for the error term. So I'll sort of confine myself to things of this type then. So it may not be true that we have an infinite series of Bessel functions representing the summatory function, but we might have an infinite series representation for a weighted sum. So in other words, for nu sufficiently large, there might be then a representation in terms of Bessel functions. And then what we can do is actually use a differencing argument, which is originally due to Landau, to work our way down from the weighted sum for nu sufficiently large down to the sum of arithmetic function itself. Now note that this smooths things out. So this factor, x minus n to the nu, is a smoothing factor. So in a couple of ways. So generally, arithmetic functions grow. Now I realize that d of p, where p is a prime, is 2. But let's just say in general, arithmetic functions get large. And so we want to weight the arithmetic function by something small. So when n is large, this is small. And when n is small, when a of n is small, then we want to weight it by something which is large. So we're smoothing out the terms a bit in this way. And then also, we're taking a discontinuous function, the summatory function of the original arithmetic function, and converting it to something which is continuous. Yeah. Okay, so we regard this, these are often called Riesz sums or Riesz means. Now, we actually could do the same thing with the power of the logarithm. So note that if we had, we could have an identity where we have this power of the logarithm replacing the x minus n to the nu. So it has the same effect. In other words, when n is large, when the arithmetic function is large, this is going to be small. And when n is small, when the arithmetic function is small, this is going to be large. So you could also use these logarithmic sums to study the average order of arithmetic functions. But usually this is used more than this because these identities are usually more complicated. Okay, so I rescue Sun Kim, and then I ask, is there a weighted version of Ramanujan's formula for each of the two formulas? And we do have weighted versions. So here, nu is any positive integer. And so we see the formula is, of the same simplicity. And if nu is equal to 1, this reduces to the previous formula. So that occurred in this paper. And then we also looked at the logarithmic mean sum. So we only took the first power of the logarithm just because we saw that for higher powers of the logarithms, the identities were just becoming too complicated. So here is our logarithmic weighted sum. And appearing in the sum are actually Laurent series coefficients of the Hurwitz zeta function. So these give us sort of an added complication to the identity. And to actually prove that identity, we used this formula. And again, this follows from a result in my thesis, but I unfortunately never wrote it down when I wrote my thesis. And if you want to learn more about these sums, indicate these two papers. So let me now close with another photograph of Ramanujan. As I mentioned earlier, there are only 4 photographs that exist of Ramanujan. And this was taken while he was at Cambridge. And you can see that his face is more is fuller here than it was in the formula or in the photograph that was taken for his passport when he had lost a lot of weight then. So let me just tell you about, just very briefly, who these people are in the photograph. So this person is K. Ananda Rao. So he was also a student of Hardy, and he won the Smith's Prize when he was at Cambridge. He came to Cambridge shortly after Ramanujan came to Cambridge and returned to India shortly after Ramanujan returned to India in 1919. And the person standing next to him, and I always have to consult my notes on him because his name is Sadalar Sundara Suryanarayana Shastri. So he was actually a student at Oxford and became one of India's most famous philosophers. So this person here also was a mathematics student, but he was not a student of Hardy as far as I know. His name was Andriana Chetty. That's Taneti Suryanarayanan. And this is Chetty sitting next to Ramanujan. And he became very active in the independence movement and was a close friend of Gandhi. Now, so I think I'll close then with this picture and again express my gratefulness for the invitation to speak here and my gratitude for your attending my lecture. So thank you very much.